Last class we learned about Michael-Nerod relations, and also we have seen how we can get the Michael-Nerod relation induced by a DFA. Thus we showed that for every DFA there exists a Michael-Nerod relation, and one can automatically get the Michael-Nerod relation induced by a DFA. Today we are going to see how one can obtain a DFA from a Michael-Nerod relation. We shall see how to define a DFA directly from a Michael-Nerod relation, and thus we shall prove that the existence of Michael-Nerod relation is both a necessary and sufficient condition for regular languages. In the previous lecture we proved that existence of Michael-Nerod relation is a necessary condition for regular languages. We showed how one can get a Michael-Nerod relation from a DFA, and today we are going to see how one can construct a DFA from a given Michael-Nerod relation. So we need to construct a DFA from an MN relation. We can try to understand how the construction works using an example. Consider an MN relation represented by the following equivalence classes for the language L, which is the strings over the singleton alphabet set A, such that the length of the string is a multiple of 3, or 3 divides the length of the string. For example, epsilon is in the language, a cube is in the language, a raised to 6 is in the language, likewise it goes. And what is given is a Michael-Nerod relation on the set of all strings, and we know that an MN relation is an equivalence relation, and hence it must partition the entire string set into a number of disjoint subsets called equivalence classes. And in this case there are 3 equivalence classes, one represented by epsilon, another one by a, and the third one by AA or a square. And this is the set of all strings on A whose length is divisible by 3. This is the set of all strings on A whose length when divided with 3 will give you 1 as the remainder, here 0 as the remainder, and here 2 as the remainder, and these are the 3 classes. Now the question is, given such a Michael-Nerod relation for a language, how can you construct a DFA from this Michael-Nerod relation? So we need to construct a DFA. With this example we can see how it can be done. Each equivalence class of the Michael-Nerod relation is going to become a state in the DFA. So in this case there are going to be 3 states, one corresponding to each class in this. And you know that an MN relation is of finite index, and hence there are only finitely many equivalence classes, and thus we will get only finitely many states. So each equivalent class is going to become a state here. So what is the state set of the required DFA? It is the set of all equivalence classes of the MN relation. Now the start state is one of the states, right? It is nothing but the state corresponding to the equivalence class for epsilon. Whatever be the equivalence class for the null string, that equivalence class is a state, and that is the initial state. Now we need transitions, and this is how you can define transitions. You know that each state is an equivalence class. So we need to define from an equivalence class for a string x. For the simple A, what is the state to which you go? It can be defined as the equivalence class for x concatenated with A. That is an equivalence class, and hence definitely must be a state here, because the state is the set of all equivalence classes. We can see which all transitions we need here. You can see that the transition from this state on A is going to this state. Why? Because if you apply this equation from the class for epsilon, if you concatenate A, you will get A as the new equivalence class, and that is how you defined it. It is going to the equivalence class A. Now from here you can see that it goes to the equivalence class for A square. Why? Because you are already here A, so x is A, and you are looking at the transition for A. So you are getting the new equivalence class as x followed by A, but here x is actually A, so A followed by A is A square, and that is why you are defining it to that state. Then the last transition is going like this, because you verify that you are already in A square and you are looking for the A transition. If you append it here, you are getting A cube. And what is A cube? A cube is in the same equivalence class as that of epsilon, and so they two are the same equivalence class epsilon. And why? Because if you divide the length of A cube or length of epsilon divided by 3, you will get the same remainder, and hence they both are in the same equivalence class. Okay, and finally now it reminds us to say which are the final states. This is how you can define the set of final states. The set of final state is the set of all equivalence classes x such that x is an element of the language. So here a string is in the language if the string length is divisible by 3, that is the class epsilon. 0 is divisible by 3, and any multiple of 3 which comes out here, like A cube or A raised to 6, all these are coming here, right? So the equivalence class for epsilon is going to become here the final state. So which are all those equivalence classes for x such that x is a string in the language, then that equivalence class representing a state here will become a final state. And why? Because you know that if two strings x and y are related, either both are in the language or both are not in the language. So if you see that the representative element is in the language, then all the strings here will be in the language, and that is why you make this as a final state. Now we can make it more formal. This is what we have seen. Given an MN relation for a language, you can construct a DFA induced by this MN relation defined as follows. The state set is the set of all equivalence classes of the MN relation, and the start state is the equivalence class corresponding to null string, and this is how transitions are defined, and this is the final set of states. set of all equivalence classes for which the representative element is in the language. Now the question is this transition function well defined? The meaning of this question is, we are saying that if you are in a state represented by the equivalence class of x, and if you are getting A as the next symbol, you go to the state corresponding to the equivalence class of xa. This is what we defined. Now the problem here is, now you consider a string y such that x and y are related, y is related to x. Then definitely y is in the equivalence class of x, right, because x and y are related. And because we defined the transition function like this, y is an element of this equivalence class. So we are also saying that from this equivalence class for y, if you do an A, you will go to the equivalence class for ya, right? Can it cause a problem? Because you are not looking at all other strings, you are only looking at x, appending a to it, and you are saying that you go to xa. What is the guarantee that this will work for some other string y which is related to x? This is what we want to prove. So we want to prove that ya is also in the same equivalence class. If that is the case for all y in this equivalence class, then we are done. But this is very easy to prove because we know that an Mn relation is a right congruence. So whenever x is related to y, xa is related to ya, and then ya must be in the same equivalence class as that of xa. So it is a well defined transition function, and we can prove that the language of the constructed DFA is exactly the given language on which the Michael-Nerod relation is defined. We can prove it. Suppose x is a string accepted by the constructed DFA, then why is it that x is accepted? Because the processing of x from the initial state of that machine ends in a final state. So it is by the definition of acceptance, which is true if and only if the equivalence class for x, the state represented by that is a final state. Why? Because from the definition of the transition function using mathematical induction on this length of the string x, you can prove that if you start processing x from epsilon, you will end up in this equivalence class or the state corresponding to this. Induction on the length of x by applying this definition will let you prove this. Okay, and this is if and only if. Why? You just look at the definition of f. It is the equivalence class x such that x is in the language. That is, this equivalence class is an element of f if x is in the language. This is the definition of f. I am just applying the definition of f. So we proved that x is in the language of the constructed automaton if and only if x is an element of the language on which the Mn relation was defined. So the correctness is also proved. Now before we wind up, we can look at one more example. Consider an Mn relation defined as two strings x and y are related if and only if the number of a's in the string x when divided with 2 will give the same remainder as when you do it with the other string. That is, the number of a's in x mod 2 is same as number of a's in y mod 2. So the number of a's in x and y when divided with 2 will give you the same remainder. That is the Michael-Nerod relation. We can easily see that it is a Michael-Nerod relation. and the language on which it is defined is the set of all strings over AB such that string contains even number of A's. Now we have to see which are those equivalence classes for this MN relation. You can easily see that it is only two. The first one is representing all strings with even number of A's, and the other one is the set of all strings with odd number of A's. So only two equivalence classes. Now we need to apply this construction to get a DFA, and based on the definition of the state set, each equivalence class here is going to become a state. So these are the only two states. Now which is a start state? It must be the state represented by the equivalence class for epsilon. So this must be the initial state. Now coming to transitions, it is a definition. So you can easily see that from this state a transition will go to this state. Why? You can verify that epsilon concatenated with A is A itself. So the equivalence class for A. Now you can see that the B transition is staying back because you verify that epsilon concatenated with B is the equivalence class for B, which is same as the equivalence class for epsilon, because the number of A's in this string is 0 and the number of A's in this string is also 0. So when you divide it by 3, you will get the remainder as 0 for both the cases, and hence they both are in the same equivalence class, and that is why you are staying back. Now we can verify that this is a correct transition, because if you append an A here, you will get A square or AA, which is same as the equivalence class epsilon, because here the number of A's is even, here again it is even, and that is why you are coming here. And the last transition stays back in this state. Why? Verify that you are already in A. If you process a B, then this is what you are saying, A concatenated with B, which is AB, which is same as the equivalence class of A, because in both these cases the number of A's is odd. So this equivalence class, both are in this equivalence class. So this is the machine you will get, and then which is the final state? It is the equivalence class representing strings in the language. When a string is in the language, when it contains even number of A's. So which is that state? Even number of A's is the equivalence class for epsilon. So this is going to be the final state. So that is the second example. Now let us recollect what we learned in this lecture and in the previous lecture. In the previous lecture we have seen how can you obtain a Myhill-Nerod relation induced by a DFA from a given DFA. This is what we did. The Myhill-Nerod relation, induced relation, is two strings are related if and only if the processing of both of them ends in the same state. So this construction we learned in the previous lecture, and today we have seen, given a Myhill-Nerod relation, how can you get a DFA induced by it. So from this Myhill-Nerod relation, today we have seen how to construct a DFA. See, we started with a DFA, applying the construction to get a Myhill-Nerod relation, we got it. Then we applied on that Myhill-Nerod relation the construction that we discussed today to get back a DFA. So started with a DFA and ended with a DFA, and we can see that, or prove that, these DFAs are isomorphic. Isomorphic means they are the same DFA, essentially the same DFA, except for renaming the states. So they are exactly the same DFA, but the states can be having different names. That is the only difference. Then they are called isomorphic. You can go in the other way also. You start from a Myhill-Nerod relation, apply today's construction to get a DFA. Then you apply the DFA to Michael-Nerod relation that we discussed in the previous lecture to get a Michael-Nerod relation. So, we started with the Michael-Nerod relation and ended up with another Michael-Nerod relation through this path. And in that case, you can see that these Michael-Nerod relations are identical, meaning they both will have the same set of equivalence classes. Then they are called identical relations. Okay. With this, we are coming to the end of this lecture, where I am giving you a homework exercise for you to practice and understand how we can construct a DFA from a Michael-Nerod relation. Please try to solve this problem. Today, we learned about a procedure or a construction which can be used to obtain a deterministic finite state automata from a Michael-Nerod relation. So, today we proved that from a Michael-Nerod relation one can automatically obtain a DFA. So, if a language admits a Michael-Nerod relation, there exists a DFA and hence the language must be regular. So, we proved that existence of a Michael-Nerod relation is a sufficient condition for a language to be regular. In the last class, we proved that it is a necessary condition. That means every regular language admits a Michael-Nerod relation. Thank you.